And we're on. Welcome back to Grockit's Official Guide Television. We're going through the GMAT Official Guide 12th edition, question by question, and giving you not only the answers but the explanations, along with the work that you can, the math and other notes that you would take that you can follow and make sure that you understand how to do the problem. My name's Jim Jacobson, and right now we are on page 22 of the official guide, question number 12. So page 22, question 12. So that one says positive integer y is 50% of 50% of positive integer x, and y% of x equals 100. What is the value of x? And we're given some answer choices. We're given A is 50, B is 100, C is 200, D is 1000, and E is 2000. So we're given two separate equations, but we can do some simplification of each of them just to figure out what's going on here and simplify things for ourselves a little bit. So the first one, y is 50% of 50% of x, which is the same. So 50% is the same thing as 1/2. So y is the same thing as 1/2 of 1/2 of x, which we can multiply the fractions across. So we're given basically that y is 1/4 of x. So that one's a little bit simpler. The other one that we also get is that y% of x equals 100. So this is our first equation here. Our second one is that y% of x equals 100. So remember that all percents are really just fractions expressed as a ratio out of 100. So y% is the same thing as y over 100. Y% of x equals 100, which is the same thing as 1/100th of y times x equals 100. So to figure out the value of x, we have two equations now and two variables, and we can substitute the value of y from number 1 on our page into the equation for number 2 on our page to figure out the value of x. So that then gives us, we have 1/100th of 1/4 x times another x, because remember this first x here is the substitution for the value of y. That whole thing equals 100. So to get rid of fractions, of course, the first thing you can do is just multiply by their inverse. So to get rid of the 1/100th, we multiply both sides times 100. So we're given 1/4 x times x equals 10,000. We can also simplify this expression and multiply both sides times 4. So x times x is x squared, and multiplying both sides times 4 to get rid of the 1/4 fraction here on the left, we end up with x squared equals 40,000. And then we simply take the square root of each side. Just as the square root of 4 is 2 and the square root of 400 is 20, the square root of 40,000 is 200. X equals 200. That's answer choice C right here. If you mistook how to figure out the square root of 40,000, you might have ended up with choice E equals 2,000. So that one's the trap answer there. Or if you had, for example, forgotten that about the 1/4 fraction here in the original equation, you might have ended up with x squared equals 10,000, in which case choice B would have been the incorrect trap. So these are the guys to watch out for here. Okay, we'll move on to the next one. So now we're on number 13 on page 22. 22, question 13. So if s and t are positive integers such that s divided by t, or s over t, equals 64.12, which of the following could be the remainder when s is divided by t? So we're given this original equation and some answers. So we have a is 2, b is 4, c is 8, d is 20, and e is 45. So we were given the original equation here, s over t equals 64.12. So this one's a little bit trickier, of course, because we aren't really given a whole lot of other information about these things, and remainders are something that a lot of people haven't dealt with since perhaps grade school. Once they teach you how to divide things either with a calculator or just full long division, so that you don't have decimals or don't have remainders. You basically never use them again until you start taking standardized tests again. So on this one, we can say that basically when we divide s by t, it's divided evenly 64 times and then some additional fraction of the time. So, basically we multiply both sides by t. We end up with s equals 64.12 t, which is the same thing as saying that s equals 64 plus 0.12 times t. And we can distribute the t if we want, and we do in this case. So this is 64t plus 0.12t. That's a 1. So in this case, s is evenly divisible by t 64 times, and then there is some fraction of t that is basically the remainder. It's not enough for s to be divisible one more full time by t, so that actually is our remainder right there, 0.12t. Now the question, of course, is which one of these is actually the remainder? The actual answer here, the answer choices are all integers, because remainders, remember, aren't decimals. Those are the fractions at the end of long division that, or they're not fractions. They are fractions. They're fractions of the total amount, but they're represented as integers or as whole numbers. So we know that 0.12t is equal to one of these answer choices. So we need to test which one of these results in an actual integer value for the whole number here. So, and it's perhaps easier to rewrite. Let's erase that. It's perhaps easier to write it as 12/100ths t. 12/100ths t equals. So if 12/100ths t equals 2, we would multiply both sides times 100 and divide by 12 to isolate t on its own. So that would end up being t equals 200 divided by 12, which reduces to 50 divided by 3. That's not going to be an integer, so it's not going to be choice A. Let's try the second one. 12/100ths t equals 4. In this case then, oops, forgot the t. In this case then, t is going to equal 400 divided by 12. You'll notice a pattern here. And because again we're multiplying both sides times 100 to get rid of the 100ths fraction, and then dividing by 12 to isolate t, that one ends up being, we divide a numerator and denominator by 4, we end up getting t equals 100 divided by 3. Let's try the third one. We end up same beginning, 12/100ths t equals 8. So then this one is going to be t equals 800 divided by 12. And that ends up reducing. We divide both the numerator and denominator by 4 again. We end up with t equals 200 divided by 3. Now you may have noticed a pattern here. The reason none of these final results for t are coming out to an even integer is that all of them end up being these powers of 10, or not powers of 10, multiples of 10. And they're all being divided by 3. So if we're looking ahead a little bit, we can see that in order for this numerator in any of these numbers here, in order for this numerator to be evenly divisible by 3, and that 3 is going to be there because we're dividing by 12 every single time, we need whatever number is in our answer choice to have 3 as a factor, so that we can, when we divide by 3 at the end here, it ends up factoring out. The only answer choice that has 3 as a factor, 3 is not one of the factors of 8, 3 is not one of the factors of 20, 3 is one of the factors of 45, so choice E. And of course, if we'd recognized that sooner, we could have jumped right to that answer choice, or if we had started from the bottom, we would have gotten it right initially, but you can't always count on that on the GMAT. Okay. Onward to page 22, number 14. So of the 84 parents who attended a meeting at a school, 35 volunteered to supervise children during the school picnic, and 11 volunteered both to supervise children during the picnic and to bring refreshments to the picnic. If the number of parents who volunteered to bring refreshments was 1.5 times the number of parents who neither volunteered to supervise children during the picnic nor volunteered to bring refreshments, how many of the parents volunteered to bring refreshments? A fine question. A, is it 25? B, 36? C, 38? D, 42? And E, 45. Okay, so again, with overlapping sets, when we're given two groups of people, some of whom are doing both things, some of whom are doing one or the other, and then maybe some of whom aren't doing either thing, it is useful to write this down in the form of a Venn diagram. Helps us keep our numbers straight, especially because there is that differentiation between those who are doing something and those who are only doing something. So we have people who are supervising the children. We have people who are bringing refreshments. The people in the middle here are the ones doing both, and then we have some other number down here that's doing neither. So then we fill in the information, and all of this ends up equaling 84. Okay. So we know that 35 volunteered to supervise children during the school picnic. Now that says 35 volunteered, not 35 volunteered to only supervise. So the 35 is the whole circle S here. We don't know how many are doing just the supervision, or how many are doing both. 35 is the total circle. We also find out that 11 volunteered to do both. And the number of parents who volunteered to bring refreshments was 1.5 the number of parents who volunteered to do neither. So if we make the number who do neither, we can call it N for neither. The number who brought refreshments is 1.5 times that number. It's a pretty good start. We can also deduce some other numbers from this. So we can subtract the number who did both from the total number doing the supervision to figure out the number who are only supervising. So 35 minus 11 gives us 24 in this box. So 24 plus 11 gives us 35 for that whole circle. And then we basically know that all of these numbers together, 24, or let's put this another way. Normally, the formula for overlapping sets is you add up the number that are in circle number 1, the number that are in circle 2, minus the number that are doing both. You have to subtract it once, because otherwise you end up double counting it when you add up circle 1 and circle 2. So circle 1 plus circle 2 minus both plus neither. We can also do circle 1, or the inside of circle 1, the part that doesn't have the both in it, plus the entirety of circle 2, which is in this case 1.5n, and plus those that are doing neither. Now, of course, in this particular case, we're actually trying to find the value this one here, the 1.5n. So if we can reverse which variable is recorded as which, we can make our lives a little bit easier. Remember that 1.5 is 1.5 times n. So r equals 1.5n. We could also say that r equals 3/2 n, because 3/2 n is the fractional equivalent of 1.5 expressed as a decimal. Now if r equals 3/2 n, and the number we're really after is, if we want the variable to, if we want r to be the variable and the number that are doing neither as the fractional thing, so that when we solve the whole equation the whole thing is easier, we can say that n equals 2/3 r. Again, we're isolating the variable we don't want so that we can actually eventually solve for the number we do. So we add all of these together. We have the total. So the number in the first circle is 24. We can add the number in the second circle, which is going to be 2/3 r, plus the number that actually are doing neither here, which is another r, and plus 24. Oh, we already have the 24. That all equals 84. We can subtract 84 from both sides. We can add the two r's together. 2/3 r plus basically 3/3 r. A whole r is the same number, numerator and denominator. So 2/3 r plus 3/3 r, we end up with 5/3 r. Oops, that's a 60, not a 6. Equals 60. Multiply both sides times 3. 5r equals 180. And then divide both sides times, or by 5. r equals 36, which is choice B. The GMAT does like its overlapping sets because of the number of ways you can do things and the number of places you can insert variables. Okay, on to page 22, number 15. So the product of all the prime numbers less than 20 is closest to which of the following powers of 10? It's a good question. Dealing, of course, with both number properties and how to deal with exponents, as well as some straightforward arithmetic. So A is 10 to the 9th, B is 10 to the 8th, C is 10 to the 7th, D 10 to the 6th, and E 10 to the 5th. So the product of all the prime numbers less than 20 is closest to which of the following powers of 10? Of course, to start, we need to know what all the prime numbers are less than 20. Remember, prime numbers are numbers that have only two factors, that number itself and then 1. 1 is not a prime number because it only has one factor itself. So the prime numbers less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. And so we can do this as one large multiplication problem. I guess I can basically just trust you to multiply all this out yourself. Multiplication, you can do it in either order, either starting from the biggest end and going down to the smallest end, or go from smallest to biggest until you're no longer able to do it in your head. I do recommend writing down each step of the way just so that you can make sure that you are keeping track of your numbers. And actually on this one, as long as you don't mismultiply things in terms of their decimal places, even if you make a mistake along the way, the ultimate goal here is actually just to figure out the number of decimal places to the left of the decimal point that we're going to end up with. The final product ends up being pretty large, ends up being 9,699,690, which is a big number. And this is what I was saying about the number of decimal places. Really, all you need to know is how many places this takes up, because then you can say, well, this number is clearly closest to 10 million, which is the same thing as 10 to the 7th. Choice C. So again, as long as you've got the number of decimal places right and this final digit being above 5 million, rounding this up would put us closest to 10 million. Okay, number 16 on page 22. So, if the square root of the quantity 3 minus 2x equals the square root of 2x plus 1, then 4x squared equals what? Alright, so choice A is 1, choice B is 4, choice C 2 minus 2x, choice D is 4x minus 2, and choice E is 6x minus 1. So our initial expression here is 3 minus 2x as a square root equals square root of 2x plus 1 separately. And we're trying to figure out 4x squared. So we're not actually asked to figure out the value of x, and so whenever possible, if there's a way we can simply arrive at the expression that 4x squared equals, rather than figuring out what x is and then going from there, we can save ourselves some work. So one of your first steps whenever you're faced with radical signs in the equation is to get rid of them. Your life is made much easier by doing so. If we square both sides and to keep the equation equal, we have to square both sides of the equation. If we square the left-hand side, the quantity 3 minus 2x squared, when it's the square root, that simply removes the radical. So we are given 3 minus 2x on this side. On the other hand, this one here, because the whole thing isn't under the radical sign, what we're actually doing is FOIL. Remember, FOIL stands for first, outer, inner, last. It's just a mnemonic device for remembering when you're multiplying binomial things, binomial expressions by each other. Make sure that it helps you make sure that you don't end up missing anything. So we do the first terms together. The square root of 2x times the square root of 2x simply equals 2x. The outer terms, in this case, it's plus square root of 2x. The inner terms will also be the square root of 2x, so we can simplify the two of them together. That'll be 2 times the square root of 2x. And then 1 times 1 is 1 still. Okay. Now, if we can, whenever possible, we want to get these radicals isolated again so that we can square them in turn and get rid of them, because these radical signs basically make everything a lot harder. So we want to get rid of them first. We can subtract 2x from both sides. We have a 2x here and a minus 2x here. So if we subtract 2x again, we get 3 minus 4x equals 2 times square root of 2x plus 1. We can subtract 1 from both sides, so then we get 2 minus 4x equals that expression again. And now once we have a radical, and then we can divide both sides by 2. Again, we're trying to get the radical on its own, so then we get 1 minus 2x. We've divided this whole thing by 2 and gotten rid of the 2 over here. So we get 1 minus 2x equals the square root of 2x. Now it's time to square both sides again, and we're going to have to use FOIL again, curses, foiled again, to multiply the left-hand side of the equation this time. So this is really 1 minus 2x times 1 minus 2x equals that square root of 2x. Now we square both sides again. The first terms we get 1, the outer and the inner, are both minus 2x. So we add those two together, we get minus 4x. And minus 2x times minus 2x equals positive 4x squared. Remember, negative times a negative is a positive. Squaring this guy on this side simply removes the radical sign, equals 2x. Now remember, all the way back here, we are after this value of 4x squared, and here we have one in our equation. So the remaining task for us is actually to get everything else from the left-hand side of the equation over to the right-hand side. So we can add 4x to both sides to get rid of that middle term. So we get 1 plus 4x squared equals 6x, and then subtract 1 from both sides to get rid of the constant here. So then we get 4x squared equals 6x minus 1. And if you were sure, even if this had been a more complicated question, and you wanted to save yourself some time, as soon as you got 4x squared on its own and you had the 6x here, you could have said, oh, hey, choice E is the only one that has 6x. If you want to be thorough, make sure that you're getting things right, and you have time on the test, by all means do it all the way through to make sure you've done it correctly. In either case, choice E is the correct one on question 16. All right, still page 22. Question number 17. So if n equals the fraction 16/81ths, the square root of that expression, what is the value of the square root of n? So a is 1/9, b 1/4, c 4/9, d 2/3, and e 9/2. Okay, so we are given n equals 16/81, square root of that. One of the properties of exponents and radicals is that when you have the entire fraction under the radical, you can simplify it as the radicals respectively of the numerator and denominator. So 16/81 under the square root sign is the same thing as n equals the square root of 16 over the square root of 81. This looks a lot more familiar. Of course, you could still do it if you recognize that you can have squares of fractions and square roots of fractions and things like that. But if it's easier for you to do it this way, it's a tiny step and doesn't add any significant amount of time. So the square root of 16 is 4. So n equals 4. Square root of 81 is 9. Okay, so we're done, right? There's choice C right there, 4/9. Except, of course, we're not. You may remember that the question is actually asking what is the square root of n? Exclamation point, exclamation point, frowny face. So if we weren't actually paying attention, we would have chosen choice C and gotten it wrong, because there is one of those partial computation wrong answer choices. We actually need the square root of n. So the square root of n equals the square root of 4/9, because that's our value for n. And just as we did before, when you have a fraction like this, numerator and denominator, you can reduce the radical sign, not reduce, you can make it over each of the individual elements, the numerator and the denominator. So square root of n equals square root of 4 over square root of 9. And these numbers should look more familiar. 2 times 2 is 4, so the square root of n, we're leaving that where it is, so we remember that's what we're doing. That equals 2. The square root of 9 is 3. So the square root of n, choice D, is our correct answer. Okay. On to number 18. Page 22. So if n is the product of the integers from 1 to 8 inclusive, how many different prime factors greater than 1 does n have? And our choices are 4. I'm going to write them as numbers because it saves a little bit of time. B5, C6, D7, and E8. Okay. n is the product of the integers from 1 to 8, you may actually be tempted to figure out what that number is. In this particular case, though, you don't need to, because we're actually talking just about what its prime factors are and how many of them are different. It is important to remember there is a difference between distinct prime factors and just prime factors. A number can have a prime factor repeated, and in fact would if it were the product of integers from 1 to 8. But we're after the number of distinct different prime factors. So how many different prime numbers get used? Different prime factors greater than 1. I'm not actually sure why they say that, because 1 isn't a prime factor. But all we have to do basically is list the numbers from 1 to 8, because these are the numbers we're multiplying together, and then identify which of these are going to be prime. So 1 is not prime. 1's an identity. It only has one factor, so it's not prime. 2 is a prime number. Its factors are 1 and 2. 3 is a prime factor. 4 is not. Its factors are 1, 2, and 4. 5 is a prime factor, because its factors itself are 1 and 5. 6 has 1, 2, 3, and 6. 7 has 1 and 7. And then 8 has 1, 2, 4, and 8 as its factors. So whatever number 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 is, the number of distinct prime factors it has is 4, 2, 3, 5, and 7. So it's answer choice A. There are 4 different prime factors for this big number, which we shouldn't compute. You can do it on your own time if you really want to know, but on the GMAT, don't. Okay, number 19, page 22. So if k is an integer, and k is between 2 and 7 exclusive, 2 is less than k and k is less than 7, for how many different values of k is there a triangle with sides of lengths 2, 7, and k? Once again, they've written out the answer choices as words, just a tiny extra step in your thinking in some cases. So A is 1, B is 2, C is 3, D is 4, and E is 5. And we have 2 is less than k, and that's less than 7. That's a 2 rather than a z. Okay, so an important rule of triangles, which gets tested in a lot of different ways, including ones where there's no drawing whatsoever on the question, is this whole length of sides. So any side of a triangle, you should memorize this rule on the GMAT. Any side must be greater than the difference of the other two sides and less than the sum. Let me say that again. So any side, any one side of the triangle has to be greater than the difference of the other two sides, and less than the sum of the other two sides. So whatever k is, since k is less than 7, 7 needs to be greater than the difference of k and 2. Well, it's going to be. It's the greatest of all three of these numbers. But it also has to be less than the sum of k and 2. So for how many values of k, k where k is less than 7, for how many integer values of k is k plus 2 less than 7? In this case, the only number that's less than 7 but still gives us k plus 2, well, and so we actually basically need to say, well, the only number for which k plus 2 is less than, or sorry, I did this wrong. K plus 2 has to be greater than 7. That was my problem. Because 7 has to be less than the sum of the other two numbers. We can add 2 or subtract 2 from both of those. So k basically needs to be greater than 5. The only integer value less than 7 but greater than 5 is k equals 6. 6 plus 2 is 8. 7 is less than 8, so it fulfills our rule on triangles. And there are no other numbers. If we have k equal to 5, k plus 2 equals 7, we can't form a triangle with sides of lengths 2, 5, and 7. They won't actually meet to form a polygon. It'll just end up being a flat line. So there is only one number, only one value for k. So it's choice A, one value. Okay, page 23. Number 20. So a right circular cone is inscribed in a hemisphere so that the base of the cone coincides with the base of the hemisphere. What is the ratio of the height of the cone to the radius of the hemisphere? And we're given some choices. A, the ratio is the square root of 3 to 1. B, it's 1 to 1. C, 1/2 to 1. D, square root of 2 to 1. And E, 2 to 1. Time for a little art project. So imagine we have a hemisphere. Hemispheres are not going to come up very often on the GMAT. So imagine that this was a really nice looking hemisphere. And within it we have a right circular cone. When it says a right circular cone, the right just means that there's a right angle from the base to the vertex. So the cone is inscribed within this circle or hemisphere. So imagine these are solids, and it's a right angle from the center of the base of the hemisphere up to the vertex of the cone. So what this question is asking is the ratio of the height of the cone to the radius of the hemisphere. And remember, the base of the cone coincides with the base of the hemisphere. Sorry about that part over there, but imagine that it's all joined. Which means then that the radius of the base of the cone is the same as the radius of the hemisphere. Now the definition of a hemisphere is that basically it's all points that are the distance r away from the center, r is that radius, in every single direction. So the distance from the center of the circle to the edge along the bottom here is the same as the distance from the center to this edge over here. It doesn't matter that it's a cone within a hemisphere. Any shape that we had drawn that included this point here and this point here from the circle, from the center of the hemisphere, would have been the same distance, because that's the definition of a hemisphere. So really, whatever distance this is vertically, it's the same distance horizontally, and again the same distance in every direction. So it's simply a 1-to-1 ratio. We didn't need to know any formulas for cones or hemispheres or circles or even triangles. Almost kind of a trick question, making you think that there was more to it than there was. Okay, 21 on page 23. So John deposited $10,000 to open a new savings account that earned 4% annual interest compounded quarterly. If there were no other transactions in the account, what was the amount of money in John's account 6 months after the account was opened? All right, and then we have choice A, 10,100. Choice B, 10,101. C, 10,200. D, 10,201. And E, 10,400. You do need to know how to compute interest on the GMAT. It's not going to come up super often, and it's possible you could take an entire test where you wouldn't get a problem like this. But it does come up often enough that it's considered part of the material that you do need to know. So one of the things to know is that if he has 4% annual interest compounded quarterly, then he gets 1/4 of that interest each 3 months. Every quarter of a year, he gets 1/4 of his total annual interest. So every 3 months he gets 1%. So 4% annual is the same thing as 1% every 3 months. And he actually has the problem is asking for the amount of money in his account 6 months after the account is opened. So basically, and it's compounded after each quarter, which means you can't just say, well, what's 2% of 10,000. That's actually the trap or 10,000. Yeah, 2% of 10,000. That's the trap answer, choice C. Because it's compounded, that means that we figure out what the 1% is after the first 3 months, and then we have to do 1% of that new value for the second 3 months. So he gets interest on the interest that he just earns every 3 months, or has just earned. So we already know, we already improved our, even if we didn't have time to answer the rest of the question, we improved our odds of guessing to 1 in 4, which makes our life easier. So for that, it's just a straightforward math problem. We take 10,000 and we multiply it times 1.01. That's 100% plus 100% of his principal plus the 1% interest. Multiplying that all out, I'll just save you the trouble. It ends up being $10,100 and no cents. And of course that one appears as answer choice A. If we didn't actually take the additional step of computing the second 3 months of interest, this trap answer would have gotten us. But we're smarter than that, so it's not that one. Our odds are now 1 in 3, and if we didn't have any more time, we could just probably guess from here. We then need to take that 10,100. That's not right. 10,100. Again, times 1.01. That's the 1% interest in the second 3 months of his 6 months. Multiplying that all out, we end up with $10,201.00, which is choice D. Again, you definitely need to understand the difference between simple interest and compound interest, and then how fractions of annual interest rates can work on the GMAT. Number 22 on page 23. So a container in the shape of a right circular cylinder is 1/2 full of water. If the volume of water in the container is 36 cubic inches and the height of the container is 9 inches, what is the diameter of the base of the cylinder in inches? At least they're clear about keeping our units the same. Every once in a while they will change units on you also. Okay, we have some interesting looking answer choices. So we have 16 over 9 pi for A. For B we have 4 over the square root of pi. For C, we have 12 over the square root of pi. D is square root of 2 over pi. And choice E, 4 times that. 4 times 2 over the square root of 2 over pi. This is a 9 here in choice A. Okay. Always helps to start with a picture whenever we're dealing with these things to make sure we get our numbers straight and everything like that. So, right circular cylinder, the right part just means that it's a vertical 90-degree angle from the base of the cylinder to the top. Okay, imagine that's a pretty cylinder. Okay, so it's half full of water. Whenever they do a half full sort of thing, it helps to write that line in there because sometimes you'll be given several different measurements and it helps to keep them straight. The volume of the water in the container is 36 cubic inches, so V equals 36 cubic inches. Cubic, not square. We also know that the height of the container is 9 inches, so this value from base to the top is 9. We also know then, since the water is half full, since the cylinder is half full, that this height of this separate cylinder, the cylinder that's just the water, this one is 4.5 because it's half of 9. Okay. And from there, we can actually figure out, and we need to figure out the diameter of the base, which is the same as the diameter at the top, and it's going to be easier for me to draw it up there. So we need D. Remember that D equals 2 times the radius. Okay, so remember that the volume of a cylinder, volume of any cylinder, I'll write it up here, volume equals pi times that radius squared times the height, volume of a cylinder. And we have some of those numbers for this second cylinder, the cylinder within the cylinder that is just the cylinder of water. So we can compute the volume of that one. So the volume the volume of water we have, that's 36, we already have that number. 36 equals pi times the radius squared, we don't have the radius, times the height, which is 4.5. We can divide both sides by 4.5 first to get just the numbers all on one side. So 8 equals pi times that radius squared. We can divide both sides by pi. Again, because we're trying to isolate the radius, because whatever the radius is, twice that is going to be the diameter, and that's the number we're after. So r squared, I'm just going to get it on the left-hand side, equals 8 over pi. We need to take the square root of both sides to get r on its own. So r equals square root of 8 over pi. And of course, this is where it gets less pleasant. Remember that with radical signs, you can get rid of the large one by putting a smaller one over both the numerator and the denominator. So we have r equals, so it's the square root of 8 over the square root of pi. Square root of 8 is the same thing as 2 times the square root of 2. r equals 2 times the square root of 2 over square root of pi. Now remember, we're not actually solving for r, and so this is, and we're lucky in this case that r, as we figured out here, does not appear as any of the answer choices. So we know we still have some more work to do. Remember that the diameter is what we're after, and that's twice the radius. So we end up with 2 times this. So d, which is the diameter, equals 2 times this, 2 times the square root of 2 over the square root of pi, which is the same thing as 4 times the square root of 2 over the square root of pi. Ran out of space there. And of course we can simplify, we can move the 5 out of the numerator and put it out in front. So then we are left with 4 times square root of 2 over the square root of pi. And remember, just as we can go the other way, if both the numerator and the denominator have radical signs in front of them, we can put the whole thing under. So 4 times square root of 2 over pi, which is choice E right there. Very often they will do things that allow you to take pi out of the equation early, but you do need to be prepared for the possibility that pi may be left in for the entire time. You treat it like any other variable. You can divide both sides by pi, add and subtract by pi. Avoid computing the value of pi whenever possible unless the answers suggest that you actually need to estimate. On page 23. So if the positive integer x is a multiple of 4, and the positive integer y is a multiple of 6, then x times y must be a multiple of which of the following? And we have some Roman numerals here. It's a Roman numeral question. Roman numeral 1 is 8, Roman numeral 2 is 12, and Roman numeral 3 is 18. Our answers are then, choice A is Roman numeral 2 only, choice B 1 and 2, C is 1 and 3, D is 2 and 3, E is 1, 2, and 3. Okay, so positive integer x is a multiple of 4, positive integer y is a multiple of 6. So multiples of numbers are taking that original number and multiplying it times positive integers. Well, positive integers because we found out that x is a positive integer. So the multiples of 4 are things like 4, 8, 12, 16, that sort of thing. We're multiplying 4 times a number of things. The multiples of 6, because we found out that, so this is x here. Y is a multiple of 6. And the multiples of 6 are things like 6, 12, 18, 24, etc. Times any number, any whole number on that side. Okay, so at the minimum, the very smallest possible number for x times y is the lowest multiple of 4 times the multiple of 6. So at the very smallest, x times y is 24. It could be much larger. We don't actually know which multiple of 4 and which multiple of 6 it is. But whatever it is also going to be a multiple of it's also going to have the same factors that 24 does. So what we basically do is we look at the Roman numerals and say which of these Roman numerals are also factors of 24, because whatever x times y is, it will also have the factors of 24 as its factors. So is 8 a factor of 24? Yes, it is. 8 times 3 equals 24. So we know that answer choice number, or Roman numeral 1 is among the correct answers. We can cross off A and we can cross off D just on that basis, because we know Roman numeral 1 needs to be one of them. Roman numeral 2, 12. Is 12 a factor of 24? It is. 12 times 2 is 24. So we know that the correct answer needs to include Roman numeral 2. We can cross off choice C, because that one does not list Roman numeral 2. Is 18 a factor of 24? No. There are multiples of 24 that 18 could be a factor of, but it's not necessarily a factor of 24. So Roman numeral 3 is not right. Therefore, we can eliminate choice E, and choice B is the one we're left with. Okay, I think we have time for one more. On page 23, let's do number 24. So Aaron will jog from home at X miles per hour and then walk back home by the same route at Y miles per hour. How many miles from home can Aaron jog so that he spends a total of T hours jogging and walking? And the answers are definitely interesting looking. We have X times T over Y. So we're not actually, we can tell by the answer choices, we're not actually going to end up with a number at the end of this. It's going to be an expression of variables. D x plus y plus t over xy, and E. Okay, so one of the issues with this is, of course, distance problems are something the GMAT does like, and one of the tricks that they like to do is, or not tricks, one of the strategies they like to do is give you distance problems where someone does one thing on the way and then something different on the way back. The thing to remember about these problems is that the distance is going to be the same on round-trip problems. So whatever, in this case Aaron, and whatever Aaron's rate is, and whatever his time is on the way there, it's going to produce the same distance with a different rate and a different time on the way back. Remember that distance equals rate times time. So distance really just gets factors out of this equation. So we find out that he is jogging from home at X miles per hour. That's his rate. And that's going to be times whatever time that is. And it's going to be the same distance as whatever he does walking at his y rate times that time. Now, of course, we can't use time for both of these because these are actually different times. Even though the distance is the same, the time is not. So let's call his jogging rate is x, and let's call his jogging time, j, equals his walking rate. Now remember, his jogging time plus his walking time are going to add up to his total time, t. Remember, that's what we're trying to figure out, and that's what t represents in this equation. T is the total time jogging and walking. So whatever time he spends jogging, the time he spends walking is his total time, t, as expressed by the problem, minus the time he actually spent jogging. And from here it becomes an algebra problem. We're left with xj on the one side equals yt minus yj. And we can get the yt on its own, because remember we're trying to we're trying to get this isolated here. We can get the j's on the one side. So xj plus yj, we added yj to both sides, equals yt. We can factor out the j times x plus y equals yt. And then we can figure out that his jogging time on its own, j, equals that yt divided by x plus y. Of course, that's not the answer we're actually looking for. We just figured out his jogging time. We actually want to figure out how many miles he can travel. So his distance that he can travel jogging, or really any of them, but his distance is going to equal his rate, his jogging rate, which we already know is x, times his jogging time. Remember that j equals his jogging time. So x times j equals the distance that we're after. And we just established what j is. So we have x times the value we had for j, yt over x plus y, equals d. And then we just include this all in the numerator. So x times yt times this quantity, all that stuff. That ends up being xyt over x plus y equals that distance, which is choice C. Okay, I think that's enough for this particular session. Thanks again for joining us for Grockit's Official Guide Television GMAT Edition, where we go through the official guide. My name's Jim Jacobson, and I hope to see you next time. Well, I won't see you, but, you'll see me.